Welcome to the fourth week of the course in machine learning. This week has the title Inductive Learning based on symbolic representations and weak theories. So first I want to make some comments on the title of this week. So inductive learning is kind of self-evident. So why is it called learning in symbolic representations? So as I hope you have already understood, there is for a long time been a balance in artificial intelligence between work based on symbolic representations and work on sub-symbolic representations. And by symbolic representations is meant symbols, lists, semantic networks, Bayesian networks, production rules, logic, decision trees, many of those things that we introduced last week. In contrast to that, we have sub-symbolic representations, neural networks, genetic algorithms, binary strings, and you also heard something about that already. And for any part of artificial intelligence, if we look over the years, the focus of work has been on one or the other. And it has gone a little up and down. At the moment, in machine learning, there is a very strong focus on sub-symbolic representation, in particular neural networks. But that does not mean that all the other work, all the other streams of work are dead or drying up. All the different approaches continue, but at any point in time, the limelight is one of them. What is important to say is that independent if you have a focus or one or the other, symbolic or not sub-symbolic, there is also a common denominator here. In all cases, and that's mathematics, because both camps can really describe what they do more or less purely in mathematics, and mathematics is the foundation for both these approaches. So anything regarding groups and numbers and sets and graph vectors, matches, sensors, so to say, is relevant under all circumstances. But essentially this week we will still focus on symbolic representations. So let me now just try to explain the reason for the last part of the title, Learning in Weak Theories. And the motivation for including that part in the title is that there are clearly two categories of work in machine learning. So I would say the largest amount of work has been put on what is termed here learning in the presence of weak theories, in the meaning that this is creating abstractions from sets of instances with a minimal, very weak or almost absent model or background theory. Of course, there is always some background knowledge. I think we already talked about that for many of the methods and algorithms we are studying. There are a lot of parameters that have to be set. We have talked about biases that can be included into the languages we use and so on. And of course, all these things, these biases, these parameters, these things constitutes background knowledge. And we cannot never be entirely without it. But in many of the cases we studied up so far, and many cases we will study this week, there is very, very, very little such knowledge. So this means that we more or less entirely learn the abstractions by generalization from the instances. But typically also, in order for this to work, we need normally pretty large sets of instances. So that's the scenario we are focusing for the moment. The opposite situation, which we will go more into coming week, is how you can create abstractions, but also modify abstractions on the border of an existing model or background theory that is more substantial. It could be that it's almost complete and just to be adapted slightly, or it can be always partial and need to be extended. In these cases, you may have a lot of example instances, but these techniques could also work with smaller set of instances because there is so much guiding knowledge for actually guiding the way the abstractions are formed. So this is the reason for this distinction. So this week we will still focus on induction in a weak theory scenario. I will now give you a very brief overview of what's going to happen this week. So we will have 4 lectures, apart from the last tutorial lecture concerning the assignments. And these 4 lectures has the following themes. So the first is generalization as such, which is a classical abstract framework for describing how generalization can be performed. Secondly, we will look at learning algorithms for decision trees further. Decision trees was introduced last week as a formalism. Now we will look into some algorithms in that area. After that, we will turn to instance-based learning. And as mentioned on an earlier lecture already, instance-based learning is the approach where you actually not explicitly store or build up any abstractions, rather that the abstractions are implicitly defined by the way we structure our memory of instances. In all these 3 cases, we primarily focus on supervised learning, which means that the instances we look at are all labeled, typically with a class label. And also, we also partially looked at the case where we have a numerical output, which is what we call regression, but still is supervised. In contrast to that, we will finish the week with a lecture on what is called clustering, which is one of the type of techniques that are crucial for the situation where we have unclassified input, the situation that we here on the course have termed unsupervised learning. So in the first of these lectures, generalization as such, we will introduce a very general framework introduced by Tom Michel many years ago. And one can say that this is an interesting framework because in a very abstract way it tries to illustrate what happens when generalization takes place. Doesn't matter whether it takes place in one formalism or in another. And we will spend some time on looking what representation we can use and discuss that. And then we will spend most of the time of what is termed data-driven strategies for generalizations, which is essentially where we start from our instances and we actually, based on a walkthrough, a breadth first, walkthrough of the instances, but in order to find the solution, make a search of hypothesis space that we built up. And then we can do that either in a depth first manner or a breadth first manner, or in a kind of combined approach, which is still called the Wurzen space. So this will be the first lecture. So next lecture will be about decision trees. We will study a specific category here, which we call TDIDT, which is a nice palindrome, by the way, but which means top-down induction of decision trees. We will look in more detail on a particular algorithm that's been important for this area, called the ID3 algorithm, and we will discuss a few crucial issues around the application of that algorithm. The third lecture is about instance-based learning then, meaning looking at learning techniques where we essentially store all instances but don't not build up any abstractions. And essentially this lecture have two parts. The first part is around one kind of algorithm, which is called the k-nearest neighbor algorithm. And we will discuss the properties of this kind of algorithm. In the second part, we will study some machine learning schemes that are very important today because there have been many successful applications. They are discussed here because methodologically they go very well together with the instance-based learning approach. And actually the first part here is something called linear classifier, which is the basic kind of machine learning strategy, and then a particular form of linear classifier, which is term support vector machines. Finally, we will look into some specific techniques which called kernel methods that we will apply to the linear classifier in order for that kind of approach to also be able to handle nonlinear cases. The last lecture will be about cluster analysis. And cluster analysis being a technique that need to be applied typically in the first stages of an unsupervised learning scenario, where we have to look at large sets of unclassified examples. Essentially, there are many approaches in this area. I think it's been said that there are more than hundreds of algorithms that try to solve the clustering problem. What we will do here is we will try to sort these all these approaches into 5 categories: partition-based, hierarchical-based, density-based, grid-based, and model-based. And I will try to, in a pretty summarized fashion, give you a picture of the approach for each one of these categories. So this was the end of this introductory lecture. Thanks for your attention. We will continue with the next lecture on the topic of generalization as such. Thank you very much.